Yeah. Oh, and another announcement is, I think this Saturday we are following the Tuesday's timetable because there was a mid-sem break that was there. And so to compensate for those classes, we are following Tuesday's timetable. So Tuesday is the dreaded day, right, for us, 8:30 in the morning. So I'm just thinking like maybe instead of starting at 8:30, we could start at 9, if that is okay for all, right? So is there any concern, like does anybody have an issue? We'll do it from 9 to 10. So it's a Saturday, so I hope the usual commitments that, I mean, initially we wanted to do it a little later, but I think some people express they have some other commitments. So I hope since it's a Saturday that those kind of commitments won't be there. So please let me know in case you're not okay with this time. So unless somebody says something about it, I'm going to keep the class at 9 o'clock on Saturday, okay? 9 to 10. Okay?
Yes, ma'am.
All right. So, so the screen is shared and I think the recording. So today what we are going to do is we'll start with constrained optimization. So just to give a recap of how the course has gone, like initially we looked at unconstrained optimization, where there was a function that you wanted to minimize and there were no constraints. So basically you were looking at all of the real space. Okay, if it was in n dimensions, it was in Rn, and you were trying to minimize a function over Rn. Okay, and then we saw some approaches there. And then we were preparing to move towards constrained optimization. So that's when we looked at convex sets, convex functions, to look at also convex optimization problems. Okay, and then in preparation to move towards constrained optimization, we looked at linear programs. Okay, which is a very special form of a constrained optimization problem, in which all the objective is linear and all the constraints are also linear. Okay, so because of this linearity, there were some things you could exploit there, and the simplex method, in fact, made use of these linear form of the constraints and the objective. Okay, so then there were some other nice properties, like one of the extreme points or the corner points of the polytope, one of the corner points of the feasible region, that will be an optimum point. So that was something which we made use of. And then we looked at duality from the purview of LPs. Okay, so now we're going to a general framework of constrained optimization where there's not this kind of a structure is not there. Okay, it can be anything. This F can be anything, and this set can be anything. It may not be convex. It may not be linear. So you're going to look at this problem in complete generality now. Okay, so of course there are various settings in which constrained optimization becomes relevant. So I've just listed just very few examples here. So first is something like these are problems which you probably dealt with in your 12th. So what's the box of minimum surface area, but you want to ensure that it has a volume V. Okay, so if you're trying to manufacture some boxes, but you want to ensure that there is a pre-specified volume, what is the minimum surface area, so that you need the least raw material. Okay, so that is a constrained optimization problem. Now it also shows up in machine learning and several models. You probably might have seen some examples. So things like the maximum likelihood estimators that you have. So just to give you a very simple example, like you have a lot of documents, right? This natural language processing kind of area where you need to do some kind of classification of some documents. And now each of these documents, you'll have a lot of words, and you're interested in finding what is the probability of occurrence of each word. Okay, so what you're trying to maximize is it's a likelihood of seeing these data. You have some data, you have these documents and the occurrences of words, and you want to maximize the likelihood of seeing this data, and you want to find the parameters. So it's a probability distribution over the words, and the fact that the parameters are probability distributions, that comes up in the constraints. Okay, so that's one example, and of course that is a starting point, and many things you build over this problem. Okay, like things like topic models and even PCA. Those are some of the models where it really plays a role. Constraint optimization plays a role. Okay. Now I know there are some people from electrical who are in this class. So one example which could be of relevance for you guys would also be this problem of circuit design. So where you want to there are some parameters with which you are going to design a circuit, and you want the circuit to have minimum area, for instance, and of course you also have some other metrics that you want the circuit to satisfy. Okay, so yeah, it's very loose statement coming from a computer science engineer. So, but of course, I think you will be able to relate it to something that you are seeing. Okay, it shows up everywhere, and that's the gist of it. Constrained optimization, and there are different classes or categories of constrained optimization. So one of them is these LPs, which we already saw. Okay, and where the objective is linear and the constraints are also linear. Now, there's another class of constraint optimization called quadratic programs, where the constraint is still linear, like in LPs, but the objective is a quadratic form. So there's an optimization problem over X, and the objective is something like this: X transpose QX plus C transpose X. Okay. So this is called quadratic programming. Now you could also have problems where the objective is quadratic and also the constraints also have a quadratic form. Okay, so these are called quadratically constrained quadratic programming problems. It's QCQPs. Okay, so these are some examples. Of course, there are it's a very big set of problems. So this is just to give you some sense of the kind of problems that come in this class. Okay, so now how do you solve these constrained optimization problems, right? Before we get into specific techniques, one way is you already know unconstrained optimization by now. So is there a way you can transform constraint problems to an unconstrained framework? So it turns out in some cases you can do it. Okay. So an example is this. So suppose you have a function you want to minimize over x1 and x2, subject to x1 being greater than or equal to 0. Okay. So now one way is you can, instead of writing it as a form of x1, you can make the substitution that x1 is some y1 square. Okay. That will ensure that x1 is greater than or equal to 0. And now, wherever x1 comes in the original problem, you just replace it with y1 square. Okay, and so this is now an unconstrained problem. And yeah, whether it is easily solvable or not, we don't know. It depends on the function and the kind of coupling that's there between x1 and x2. But this could be one way to try and see if the problem has a solution. I mean, if you can solve it, naturally. Okay. Now, another case is when you have x1 strictly greater than 0. So, of course, we try to avoid formulating problems in this way, because at least as far as the solvers are concerned, I mean, these are all like they're ill-posed in the sense like you may not have a minimum also in these kind of problems. But anyhow, one way you can try to reformulate this as to write x1 as e power some y, and now wherever x1 comes, you replace all occurrences with e power y, and the variables are now y and x2. So this is some ways to do it. Okay, but again, there's a word of caution here. It may not work out always. Okay, so it's not a general formula that you can use, and you're not guaranteed that it will work. Okay, so to see some of the difficulties associated with this kind of approach, let's just take this problem. Okay, so minimize x1 plus x2, and now you have an equality constraint. X1 square plus x2 square is 1. Okay, so now one thing is, when you have an equality constraint, maybe you can write x2 in terms of x1. So there are two ways. So x2 square becomes 1 minus x1 square. So there are two possible values of x2. So it's either the positive square root of 1 minus x1 square, or the negative square root. Okay, so now you have to be careful here. So you're going to get two problems here. So one would be min x1 plus square root of 1 minus x1 square. And the other one is going to be minimize x1 minus square root of 1 minus x1 square. Okay, so one subtle point that happens here is that, a constraint like this, x1 square plus x2 square equals 1, implicitly it's ensuring that x1 is taking a value between minus 1 and 1. So implicitly x1 will be less than or equal to 1 and x1 will be greater than or equal to minus 1. Okay, but that is something that we don't take care of in when you convert it to an unconstrained problem. So that doesn't have this kind of a thing. Of course, in this problem, the square root of 1 minus x1 square, so that becomes meaningless. You'll get imaginary parts and all that if x1 takes a value which is less than minus 1. Okay, but anyway, that is something to be careful about. So it's truly not an unconstrained problem if you look at it. Okay, but anyway, if you decide to anyway go ahead with this, what you're going to get is, one thing is when you observe this problem, this is actually a concave function. You're trying to minimize a concave function. So something like, if you try to plot this, you will get a function like this. Okay, so this is the x. Sorry. So this is x and this is the value of the function. So you'll get something of this kind. Okay, so the minimizer actually, it is in true sense, if you do an unconstrained problem, I mean, if it's an unconstrained optimization, it's actually unbounded. Okay, but you can try to find the critical points. So let's just do that. So can you tell me? So I'm trying to set, this is my new f here, and I'm trying to set f dash x1 to 0. So can you tell me the gradient of this function?
1 plus
1 plus
1 by 2 minus 1 by 2.
Okay. So 1 plus, so let's just do it. 1 plus 1 by 2 times square root of 1 minus x1 square, right?
Minus.
Yeah, into minus 2x1, right? So this is going to be the derivative and you would set this to 0. So this would give you something like x1 is equal to square root of 1 minus x1 square. Okay, so here it's as if x1 is plus square root of 1 minus x1 square. So now when you take the roots of this, I mean the value of x1 which solves this, can you tell me what it would be?
1 by 2.
So x1 square
is equal to 1 minus x1 square.
Yeah, sure. So that would give you, when you take it to the other side, you get x1 square is 1 by 2, right? Yes. So here, it's very tempting to just take it as x1 is plus 1 by root 2 and minus 1 by root 2. But actually minus 1 by root 2 is not a valid root here. So if you even bring it back here and substitute, you will see that you won't get a 0 value. So the only value is x1 is 1 by root 2, the positive one. And x2, since we took it as x2 is plus square root of 1 minus x1 square, so this is also going to be 1 by root 2. Okay, so these are the critical points for this function. But this is a concave function, and this is actually turns out that this is a maximizer. Okay, and so I leave it as an exercise for you to evaluate the second derivative and see that it's see what it gives you. But anyway, so this is not a minimizer, and it turns out that because x1 has to be greater than or equal to minus 1, if you plot this and see, you will see that the actual minimizer is x1 is minus 1. And x2 is square root of 1 minus x1 square, so x2 becomes 0. Okay, so based on this problem, based on this part, you're going to get minus 1 and 0 as the minimizers. Okay, so you see that those are not even critical points, and there are some difficulties in solving this kind of a concave minimization problem. Okay, now similarly, you can see what happens on this side. Okay, for this problem where you said x2 is minus of square root of 1 minus x1 square. So I leave that as an exercise. But you see there are these complications here. And if you look at the region, it is a two-dimensional problem. So you can try to see it geometrically, what it gives you. So I've just drawn the figure geometrically. So the constraint was x1 square plus x2 square is 1, right? So that is actually this circle that I've drawn in red. So this is a point 1, and here also is 1. So this is x1 and this is x2. Okay, so the circle, only the boundary of the circle, that is the feasible region. And the objective is x1 plus x2. So these are the contours. The blue lines are the contours. Okay, so now if you take this point, plus 1 by root 2 and plus 1 by root 2, that is somewhere here. The one I've drawn here. And the value of x1 plus x2 at this point. So this is 1 by root 2, 1 by root 2. And the value here is actually root 2. So it's a maximizer for this problem. Okay, and the function value decreases along this 0. And if you look at a point here where x1, so this is minus 1 by root 2 and minus 1 by root 2. So here the value of the objective is just going to be minus root 2. Okay, and turns out this is the minimizer. But from here, if you look at this objective in this part, the minus 1, 0 is something here. Okay, so that is not, you can, I mean, this, it doesn't, I mean, you're not getting a correct answer if you only look at this part. Okay, and you have to also see this side, and you will get this point ultimately. But there are a lot of these steps and these subtle issues that you have to deal with when you transform the problem to an unconstrained problem, and you have to be really careful. Okay, so we don't want that kind of thing, because it's not a very, it's not very general. It's not a very general approach you could have. And in fact, I mean, this is one case of an equality problem where you can write x1 as a closed form or x2 in terms of x1, but many times you may not even be able to do that. Okay, so that's what motivates us to go further into to learn constrained optimization as a separate class. Okay, so any questions till this point?
No.
No? Okay, good. So I just want to hear from the others that you're all with me. So can I hear from some more people? Any questions? Okay, fine. So okay, so yeah, so the reason for you going for a separate study of constrained optimization, separate study of this should be clear. So in general, what we earlier said is that, the algorithms that we analyze, we will initially start off with some x naught, okay, some initial point, and you try to iteratively optimize the value of f. Okay, so at each step you're trying to get a better point. Okay, so this is what we this was the framework of unconstrained optimization problems we looked at. I mean, the same framework also holds for constrained problems, just with the difference that, at every step you have to ensure that you are also feasible. So the new xk plus 1 should also lie in this omega. Okay, so for unconstrained case, we had that, you just needed to check for the criticality, that gradient of f at x star, the optimum point, that was 0. And you also had these second order conditions. So what do these conditions, what are the equivalent conditions for constrained optimization problems? Okay, so that's what we will focus on next. Okay, so let's just get some ideas about the local min right here. Okay, so if you recall, we talked of local minimizers, where we said that, x star is a local minimizer if there is a ball around x star, in which, if you evaluate the function value, you're going to have that fx star is always less than or equal to fx for everything in that ball. Okay, now for the constraint case, you also have to ensure that, the ball intersects your feasible set, and this relation holds only for all x which are in the ball and which are also feasible. Okay, and similarly, the same notions hold for strict local min as well. So in terms of this schematic figure that I've taken here, so this is a function you want to optimize, and you're trying to optimize it in this interval, A, B. Okay, so now it's not an unconstrained problem. So in terms of local minimizers, of course, these are all local minimizers. We had seen this earlier. Okay, and these points here are local maximizers. Okay, now additionally, these endpoints, right? Since you're looking at a constrained optimization problem, at this point A, right? So if you look at a small region around this, so a ball around this would be a small interval around A. And now you're only interested in the intersection of that with the feasible region. So it's this part. Okay. So in this part of the ball, you can see that, if you evaluate fx star at this point A, that's going to be less than other points. Okay. For all these points, the function value exceeds. So this is also going to be a local minimizer. So for the constraint problem, it's a local minimizer, but whereas for the unconstrained problem, it was not. Okay. So similarly, at this point here, you have a local maximizer by the same logic. Okay. So these are some of the things that we additionally have to take care of, because these are at these points it matters whether if you can't look at these regions outside this ball. I mean outside the feasible region. Okay, so that these kind of ideas will be made use of when we talk of the optimality conditions. So in general, this feasible directions, we'll define what are called feasible directions. So at any point, okay, take some point x. Okay, so you say that D, a direction D is a feasible direction if there is some ball around this. Okay, such that so this D is the one that you want to see is a feasible direction. So this is the vector D, and if you make a step along the direction D, you will be guaranteed to find some point. So this is the x plus alpha D. Okay, some step along this direction will result in another feasible point. Okay, so that's if you can find a direction, if you can find a point like that, then that is what is a feasible direction. This D is a feasible direction. A step you take along the direction D will ensure that you get a feasible point, will ensure that you get another point within omega. So omega is the set which I've shown shaded here. Okay, all of this. Okay, so that's the feasible direction. And we also know descent directions from earlier. So we know that, if D is a descent direction, if there is a ball around this X again, so such that if you make a small step in this direction, then the new point X plus alpha D that you get will take a lower function or will take a lower objective than f of X. Okay, so that's what is a descent direction. And we had this in unconstrained framework. And this is something that we introduce afresh for the constrained optimization framework. So what you want to see is that if x star, if some point is a local optimum, then you cannot have a feasible direction as well as a descent direction. So that means there is no D such that which is both a feasible direction and simultaneously a descent direction as well. Okay, so in the unconstrained case, we only said that there is no D such that it's a descent. So here you need to take care of these feasible directions also. So is this clear so far? Are there any questions?
Clear, ma'am.
Clear? Okay. So what about the others? Can I hear from some more people? Harsimran? Sure, clear. Okay. It's clear?
Yes, ma'am.
It's clear? Okay, good. Okay, so let's just see how we make use of this further. So this concept of feasible directions, it leads us to something called these active constraints. Okay, so suppose you consider a problem like this where you're trying to minimize a function and there are a lot of inequality constraints. Okay, so gix less than or equal to 0. So maybe there are some m constraints. Okay, so so we say that this a constraint gix less than 0. So we say that that constraint is active if you have gix bar is 0. So the constraint is active at x bar If at x bar you see that this inequality is satisfied with equality. Okay, gi x bar is equal, it's exactly equal to 0 at x bar. Okay, so if you have that, you say that this constraint is active at that point. Okay, so anything which has, so you'll have some constraints which are equal to 0, and maybe you have some which are strictly less than 0 at x bar. Okay, so out of that, the ones which are exactly equal to 0 are the binding or active constraints. And so if you don't have this, then you will say that the constraint is inactive. If it's not satisfied with equality, you say that the constraint is inactive at x bar. Okay, so so the reason is you'll see that these play the greatest role in constrained optimization problems. Okay, so okay, so for example, in this earlier the schematic figure that I told you here. So here you were trying to optimize the functions. This was the function such that x is greater than or equal to a and x is less than or equal to b. Okay, so that was this region. Okay, so now at the point x equal to a, this constraint is active and this is inactive. Okay, and at the point x equal to b, this is the constraint which is active and this other constraint is inactive. Okay, so so this is what is for when you have inequality constraints. Now, in general, you will have also equality constraints. So a general optimization form has many inequality constraints. So GIX less than or equal to 0 and several equality constraints. Okay, so when we write down the active constraints at some point x bar, you will write all the constraints, the inequality constraints which take a value exactly equal to 0. And also you will include the equality constraints because those anyway take a value, those are always equal to 0. And in fact, those are active for every point. For every feasible point, these are active, the equality constraints. Okay, so this is the notion of active constraints. So let's just take an example here. So I'm looking at this function. So x1 minus 4 square plus x2 minus 8 square, subject to these constraints. X1 is less than or equal to 4, x2 less than or equal to 6, and 3x1 plus 2x2 less than or equal to 9. Okay, so in terms of our notations that we have assumed, it's not very critical, but it's good to get used to one kind of notation so that all the formulations become clearer later on. Okay, so in terms of this form, you will say that x1 minus 4 is less than or equal to 0. That's how you write it in this form. And g2x corresponds to x2 minus 6 less than or equal to 0. And g3x is, okay, 3x1 plus 2x2 minus 9 is less than or equal to 0. Okay, so basically I wanted everything in the less than or equal to form. That's what I did. Okay, so now in terms of the feasible region, if I draw it geometrically, so first constraint is x1 less than or equal to 4. So this is x1 and this is x2. So what I'm going to have is, this is the line x1 equal to 4. Okay, and so everything to the left of it. So it's basically this part of the line. Now x2 less than or equal to 6. So x2 equal to 6 is this line here that I've drawn in this part. So this is x2 equal to 6. So everything below this. Okay, and now when you take 3x1 plus 2x2 less than or equal to 9, so that's the line I've drawn here, and it turns out it's this part. Okay, so by now I think these are all linear constraints, so you know to draw these regions. Okay, so the feasible region is basically everything in blue that I've written. And in terms of the objective, it's x1 minus 4 square plus x2 minus 8 square. So, so x1 is 4 and x2 8, so that is this point. So all circles around it. Okay, so so the contours will look like something like this. Okay, so at this point, it's the f of x is 0. So it starts increasing in this as you go away from the center along this, along radially outwards, the function value increases. Okay, so these are the contours. Okay, so now let's just try to see which are the active constraints at some point. Okay, so is this clear, like the geometry of this problem?
Yes, ma'am. But shouldn't G3 also be written as 3x1 plus 2x2 minus 9 less than equal to
Yeah,
0?
yeah. In strictly in this form, when you write it as less as -9 is less than or equal to 0. That's right. So I just wrote it now for main thing. I was just looking at this less than or equal to part, and that's fine. I mean, yeah, you ideally you write it in this way, G1,
Yes,
G2, and
ma'am.
this is the right way to do it. Okay,
Okay.
so yeah. Okay, so now yeah, let's try to write the active constraints at the point, say -8, 6. Okay, so -8 is somewhere here. So maybe somewhere here, this is -8 and -8, 6. So this point. So can you tell me what are the active constraints here? So these are the three constraints, G1, G2, and G3. So can you tell me which of these are active at this point?
All three, ma'am.
Uh, so if you look at x1 less than G1, if you take the value of x1, which is -8, is strictly less than 4. It's not satisfied with equality, right?
Oh, okay.
So the active constraints are the ones which are satisfied with equality. Okay, so at the
G2
point
is then
-8,
active.
6, yes,
G2 is active then.
yeah, only G2 is active. Okay, and G1 and G3 are inactive. Okay, uh, so it's very easy to check this, right? You just evaluate this function the left hand side, see if it's equal to 0 or not. Okay, so again at -1, 6, what happens? Can you tell me? -1, 6 is yeah. Can you tell me what are the active constraints at -1, 6? So these are the constraint values. So
G2
it's
is
G.
active and so is G3.
Yeah, exactly. So G2 is active and G2 and G3 are active. Okay. So I hope it's clear how you got this. So G2 of x, so if you evaluate it at this point, you will get 6 minus 6, which is 0. And if you take G1, if you take, you will get -8 minus 4. The left hand side is -8 minus 4, which is strictly less than 0. So G1 is not active. Now G3, if you take, you're going to get -24. Sorry, that's -8, right? So -1, 6. So -3 plus 12 minus 9. Okay, so that gives you 0, and that's exactly equal to 0. So that's where these are active. So can somebody tell me again, just one more point? So 4 and -9. Can you tell me what is active?
G1 is active.
G1.
And that's it, I think.
Right, so 4 and -9 would be something here, right? Like at this point. So yeah, only G1 is active. Okay. So I hope this is clear, right? Like how you compute the active constraints. It's just a matter of substituting and seeing which gets satisfied with equality. Okay. It's clear to all? Yes. Okay. Yes. Okay. Cool. So now let's just move on and see what happens. Why are these constraints important? So it turns out that these are the ones which really need more attention. Okay. So suppose you're looking at this constraint problem, minimize fx such that x in some set x. Okay. And so what happens if the optimum is in the interior? Okay, so by interior, what is going to happen is none of the constraints are active. Okay, so an interior, you recall that point is an interior point if you can have a neighborhood around it which is fully contained in x. So if this is an interior point, this is an interior point because you can draw a ball around it which is fully contained within x. Okay, so at this point x star, suppose this is an optimum point. Okay, so is there something we can say? Okay, so one thing to note is the moment x star becomes an interior point, none of the constraints are active. Okay, so every constraint is getting satisfied with an inequality sign. It's strictly less than or equal, less than form. Okay, so what it means is gi x star will be strictly less than 0 for all the constraints. Okay, so that's what is an interior point. Okay, so at this point now, if you see, so if this were to be an optimum point, then you remember our, the things about descent directions, right? Like what we just saw some time back. So at this point, every direction you go along is going to be a feasible direction, right? You can make some small step along every direction. Whatever direction you take, you can make a small step and still remain within X. Okay, remain within capital X. Okay, so every direction is feasible. So in some sense, it's quite like an unconstrained problem itself, right? Because you remember in unconstrained problems, there was nothing of a feasible set. So every direction you went was feasible by default, and you only cared about descent directions. So if some point x star is an optimum, then it would satisfy the necessary conditions for an unconstrained problem. Okay, so it would have to be that gradient of fx star is 0, and this is all that is required. Okay, you don't have to really worry about anything, about any of the constraints. It's as if the constraints don't exist, because within a neighborhood, you're always guaranteed to find a feasible point. Okay, so but whereas if you had a point here, okay, so if x star was somewhere at this point, which is on the boundary, so at this point, yeah, this constraint is active. So there are 4 constraints as per the region shown here. So each of these curves, let us say those are the constraints. Okay, and this was going to be, suppose you say that this is going to be an optimum point. Now you have to think a little bit, because all these directions are not going to be feasible. Okay, so only these set of directions, which, like something like this, within this, okay, only those will be feasible. So, I mean, not every direction will be feasible. So you cannot use your usual unconstrained minimizer condition for these points if this was an optimum. Okay, so that's why these active constraints play a role. In fact, for this kind of a point, it's only this constraint, so this curve. So this is the active constraint here, and that is the only one which matters for this point. So in terms of these constraints, these are inactive. So this is inactive, this is also inactive, and this is also inactive. Okay, because it doesn't exactly lie on this curve. Okay, so those actually, you will see that those don't matter. Okay, so is this notion clear? Are there any questions on this part, like this idea that I've mentioned? Guys? Clear? Clear? Okay. You're all very quiet today. I'm only hearing from Rohit. Yes. It's clear? Clear? Okay. All right. So this idea is going to be useful of active constraints. Okay, so now let's just go to an example. So we are now ready to, understand a bit more about what happens to these problems. So let's just take a problem like this: minimize x1 plus x2 such that x1 square plus x2 square minus 2 is 0. So here these are equality constraints. So let's just focus on this case for now. Okay, so the feasible region would be again something like this, right? So let me just draw it. So this is x1, this is x2. Okay, and I have this is the circle. I mean, the feasible region is exactly a circle, and this point here is what is this point? Can you tell me?
2, 0.
So x1 square is 2, so this is root 2, like
Oh,
so,
sorry, root
plus
2.
root 2, and so this is minus root 2, and here you have again root 2 and minus root 2. Okay, and of course this is very similar to the problem we saw a little while back. It's just the circle is a little bigger, and x1 plus x2, so the contours will all be like lines. So this is x1 plus x2 is 0. okay, and it increases in this direction, okay, and it decreases along this. This is the direction of decrease. So you can go on decreasing it till you hit something here. Okay, so there'll be some point here which is the optimum. Okay, so so one thing I want you to just see at this. So in there's only one constraint and it is active at every point, every feasible point. Okay, so now let's just take this point. A is -1, -1. Okay, so it's actually this point here. Okay, and the objective, so at A is -1, -1. So can you just tell me like what's the gradient of the function and the g? So let me just write this here. So this is f of x, and this is say h1 of x is equal to 0. So h1 of x is actually equal to x1 square plus x2 square minus 2. So this is h1 of x. Okay, so now when let me just write, it turns out the gradient of all these play a role. So let's just write that. So can you tell me what is the gradient of the function at any x?
2x1 and 2x2.
Okay, so that is the gradient of h, right? So that is the equality. So that is, right, 2x1 and 2x2. So what about the function? The
1
f
1.
is this 1, 1, right? Okay, so now let's just take this point. A is -1, -1. So it's this one. So here at A is -1, -1. What happens is gradient of f is exactly 1, 1. That's anyway the same for all points. Now, if you take gradient of h1, what you're going to get is -2, -2, right? So just substitute it here. So what happens is gradient of f, let me just draw this part. I'll just zoom into this part and draw it. So the constraint is something like this, and this is the point of interest. And here the f value, the gradient of f points in this direction. So this is 1, 1. And the gradient of h1 points in this. This is the gradient of h1, okay? So it's -2, -2. So it's the same direction, but with a negative sign. So it's flipped and it's the magnitude is twice. So this is gradient h1 and this is gradient of f. Okay. So you can see that, these are parallel to each other. Okay. So it turns out that this is from the geometry, we know that this is an optimum point. And we see that this kind of thing is happening where this gradient f and gradient h are in the same they're parallel to each other. Okay, so this is one of the things that happen at optimality. So the reason is that this gradient is always going to give you the direction of increase. So suppose, so this is you are interested in the minimization. So the negative gradient is what is the direction of decrease, the direction which you should go to. Okay. But now if that direction is not feasible, then you're in some sense, that's what you want. Okay. So if you want any feasible, any descent direction here, what you would have is, you remember the condition you wanted, if D is a descent direction, so then it means that D transpose gradient of f should be less than 0. Okay, so at this point, any direction that you take any step that you take along any of these directions, if you can go, that will lead to an improvement in the function. Okay. Now, are any of these feasible? Right. So that is what this grad h lets you evaluate. So the gradient of h1 is in this direction. Now, since it's an equality constraint, you don't want you don't want any change in the function value. So h1 of x is 0 and you want that to be maintained. So the only way that you can move is along directions perpendicular. So this either this way or this way. So perpendicular to the gradient if you move, perpendicular to the gradient of h1 if you move, then your constraint is going to be maintained. Okay, but these directions will not be descent directions, because only the directions which is something in this part of the plane. Only these are going to be descent directions. Okay, so you can see that when both these are parallel, that's when I mean, if x star, if this was an optimum point, then these had to be parallel. Okay, so let's just take another point. Say, let's take this point C. Okay, so maybe something here. Okay, so -1, 1. Okay, so like we'll come to this point B a little later. So at C equals -1, 1. Okay, take that point. Okay, so now can you tell me what is the gradient of f and h1 at this point?
Gradient f is the same, and gradient h1 is -2, 2.
-2, 2. Okay, so again, let me just zoom into it like I did here. So at this point, so it is something like this. The constraint was like in this manner, and this was the point C. I mean, this is the C and F of C. And here the gradient of F is again in this direction. Now, if you take gradient of H, so it's -2, 2. So it's you remember that it's always going to be orthogonal to the contour. So this is the contour because this is an equality constraint, the contour of H. Okay, so that is exactly the curve itself, and orthogonal to that, so something like this. Okay, so this is gradient of H. So okay, my drawing is quite bad. So gradient of F is, it looks like these are orthogonal, but are they orthogonal? Yeah, they are, right? So -2 plus, yeah, so they are in the orthogonal. Okay, so my drawing is not that bad after all. Okay, so these gradient of F and gradient of H look like this. Okay, so now you're trying to have a decrease in the function value. So uh, all of these directions here are feasible. I mean, all of these are descent directions, right? Because they will have a component with negative of gradient f. So you can move in any of these directions. Now, in particular, since the equality of the constraint has to be maintained, so gradient h is in this direction. If you move in either this direction or this direction, the constraint will change. Okay, so but whereas if you move along this direction, the constraint will be maintained. The constraint h1x equal to 0 will get maintained. And in fact, that is also a direction which is a descent direction. Okay, because that if you move along that direction, the function will decrease, and the constraint h1 of x equal to 0 will also be maintained. Okay, so then it could be, I mean, so this point C cannot be an optimum point. Okay, so this is not an optimum. Okay, so it couldn't have been an optimum point because this phenomenon occurs. Okay, so I hope this is clear. I don't know if you're all following what is going on. Is this?
Similarly, the -1, -1, point, that is also not an optimum because direction exists, right?
No, so at -1, -1, so here the gradient is in this direction, the gradient of f. Now, if you wanted to have a decrease, it should be a descent. So anything on this side, I mean, this is the this is what is orthogonal to delta f. So along this direction, it is still not a descent. Okay, anything which makes an obtuse angle, right, with the gradient. So basically everything on this part, but not including these orthogonal lines.
Oh, okay. Then in this case, what is the conclusion? That we cannot move in any direction.
So you cannot move in a direction which is also a descent. You cannot get a feasible direction as well as a
Oh,
descent at the same time.
okay. Understood.
Understood?
Thank
Yeah.
you.
Good. Okay, so now you can also try to see what happens at B. Okay, so at B is, let's just do that one. At B is 1, 1. What is going to happen is, so gradient f of x is 1, 1. And the gradient of h,
Two,
so get 2, 2, right? So here also, like, so there would be something like the curve is like this. The gradient is in this way, and gradient f and gradient h is also in the same direction. Okay. So now, again, so in order to have a feasible direction, because you want h1x to be 0, it should be along the orthogonal to the gradient of h. Okay, if you move along this step or in this direction, then you will get a feasible point. Okay, but in terms of the function, these are still not going to give you a decrease. Okay, so you can, because they have to be making a negative value. I mean, they should have a negative dot product with gradient f. Okay, so all these are descent directions. Okay. So that's one thing, but one thing to note is, here both are in the same directions, but actually this point, so this point so 1, 1, so that is somewhere here, it actually is a point of maximum. Okay, so this kind of phenomena where gradient f and gradient h, they are parallel to each other, that will happen even for an optimum, I mean, for a maxima as well as a minima. Okay, so the idea is for any optimum point that will get satisfied. Okay, and it has to get satisfied. There's no other way it can happen. Okay, so I don't know if this made sense to you all. So what I want to do is in the next class, I want to formalize this. So this was just to give you an intuition. We will formally prove this fact. So what we're trying to say is delta fx is equal to mu times delta h1 of x. If x is an optimum, if x is a minima, then you have this. Okay, so this will happen for some value of mu, for some mu in R. Okay, so I don't know if this you understood these points, but anyway, we'll stop here for this class and we'll continue on tomorrow. So I'll hang back here for some time if there are questions. So otherwise, thanks everyone for being here.
Thank you, ma'am.